Hey everyone, so I thought I'd just make this video to quickly talk you through atomic spectra, maybe a slightly more visual way, and then I'll talk to you about the formula that's associated with it in as much detail as you need to know. Which actually isn't much for this one. So atomic spectra is something that we observe where we have our nucleus, um, an atom, right, which we know is made up of positive and neutral charges. Then we also have our electron rings around the outside. So I'm going to draw three electron rings here. So let's say we'll start off with a simple atom that just has one electron, right? So it might be something that's quite low down the periodic table. Um, but emission spectra will happen when a photon of light comes in and it hits this electron. So the electron then is going to have a whole lot of extra energy, and with that energy, um, it's going to jump up to a different energy level or a different orbital, right? So these are kind of like the shells of the atom, right? Or electron shells. If it has more energy, it's going to jump to a higher energy level, which actually will be further away from the nucleus. Um, this really isn't that stable. There's a reason why when we're drawing our atomic diagrams, we fill in the first shells first because they are more stable, right? So it's going to end up here. It's not going to be very stable at all, and then it's going to fall back to where it came from, so back down to its original position. Um, Now it doesn't actually move in between here and here, it just teleports, right? Because it can't exist in between them. But the word we usually use is jump, so it jumps up to here and then it jumps back, right? Um, in jumping back, because this is a lower energy level, it's going to give off energy, right? Usually as a photon. So as it falls down, it gives off energy as a photon, and then only certain wavelengths of light will actually be emitted this time, right? And what those wavelengths of light are will depend on how small or big that jump was. Um, Now, each different atom, say carbon atoms or hydrogen atoms or helium atoms, will all have different energy shells and different numbers of electrons. So the amount of energy given off will be different for them, and the corresponding frequencies will be different, just because the jumps will be different. But that's what the atomic spectra are really down to anyway. Um, we'll recap again. A photon comes in, it transfers energy to an electron, which jumps up to a higher energy level. This isn't stable, so it jumps back down. As it jumps back down, it gives off that extra energy, in the form of some light or photons. Um, the wavelength or frequency of that light will just depend on how big that jump is, and different types of atoms will give off different spectra. So just looking at one example here, we can see that the wavelengths of light given off by hydrogen are very different to the wavelengths of light given off by helium. So each band of wavelength here will just correspond to one particular drop down from a higher energy level to a less high energy level, further from the atom to close to the atom. So orange, for example, would correspond to one particular jump, might be from the third orbital down to the second, and then this turquoise color might be from the fifth down to the fourth or something. And again, they're quite distinctive for each different element. One use of this is that we're able to look at, say, different stars or different objects in space and look at the emission spectrum coming off them. And based off that, we're able to tell what kind of atoms they're likely made up of. Okay, so now we'll just go into the formula that's associated with this. This formula is specifically mentioned on the course, but is not in your log tables and is not something that has actually ever come up. I don't think you're really going to see a calculation question based off this, but you might see it come up as a short question saying list a formula that would relate the frequency of light emitted to the change in energy in the atom or in the electron shells. I think it could come up possibly as something like that. So I'm just going to go through it and make sure we all kind of know what this means anyway. Um, So I think a simpler way of writing this, or something that maybe precedes it, is just saying that the change in energy is going to be second energy take away the first energy. So what this means for our diagrams that we are looking at earlier, we have our nucleus, we have our electron shells. So let's just say that an electron here goes from this shell to this shell. Now we know that each of those shells has a certain energy involved with it, or a certain amount of energy. So we can say that this position is energy 2 and this position is energy 1. So if an electron falls from here to here, it'll give off some energy. And that change in energy is going to be the energy here, take away the new energy that it ends up with. So the difference between these two energy levels is the change in energy, or the amount of energy given off by the electron. Now the energy given off is given off as a photon of electromagnetic radiation, and we already know that the energy associated with a photon is equal to Planck's constant times its frequency. So looking at this formula, that the change in energy, or the energy given off by an electron, is going to be the second energy level take away the first energy level. We can just sub in HF. We can say HF is going to be the second energy level minus the first energy level. So we're still just saying that the change in energy is going to be energy 2 minus energy 1. But now instead of just relating it to energy, we're saying, well, what would the frequency of that light coming off it be? And this is an important formula because we kind of base our understanding of spectra, the different frequencies of light that will be given off by, say, hydrogen or helium, as we've seen before, and we base that off it. So like I said, it's not something that ever really comes up as a calculation. If it did, I'd be very surprised. But it is on the course, so I think it's important you do know it, even if it came up as a short 7-mark question or something. It'd be worth your while knowing it just for that.